In this section, we want to investigate a new kind of integral. In Calculus 1, we developed the definition of the definite integral over an interval on the x-axis between two values a and b. In Calculus 3, we developed the idea of the definite integral over a region in the plane, 2 dimensions, or in space, 3 dimensions. And now we want to integrate over curves. For example, in Calculus 1, we computed the work done in launching a satellite into orbit. Well, we integrated that simply along the straight line. However, satellites aren't actually launched along straight lines, but along curves. So we actually should be integrating along the curve. So here's a graphical representation of the line integral. We're going to take a look at this paraboloid. I made it transparent because we're going to be looking on the inside. We're going to be taking a look at the line integral over the curve given by the line segment from 0, 0 to 4, 3. I've got that drawn on here. 0, 0 to 4, 3. We're looking at the line in the XY plane. Here is the actual surface. Now what the line integral does is to give us the area of what we call the curtain between the surface and the curve. This is where we get the terminology integrating over the curve. So we're looking at going from the curve, that's in the XY plane, up to the surface. And so the area of that region is what we're looking for. Here is that region without any surface on it. So this is actually the line integral of that function over that curve. Now I've taken that same surface but drawn the curve given in parametric form as x equals t, y equals sine t. In other words, just the function y equals sine of x. So that's the red line, the graph of y equals sine of x. And so here is the curtain that's above that. And here it is with only the curtain. So that is the line integral of that surface over that curve. Now here's a little reminder of how we developed the definition of the definite integral from Calculus 1. We had a function of x that we were wanting to look at over an interval from a to b. So we partitioned the interval and we took the width of each partition, referred to it as delta x. We took any point within that partition, plugged it into the function, and we got the length of a rectangle. If we multiplied the width times the length, we got the area of that rectangle. We added all of those up from A to B, and then we took the limit of that as the norm of the partition went to 0, which also meant that the number of subintervals was going to infinity. And that was our definition of the definite integral. Similarly, in Calculus 3, we did a region that was planar, two-dimensional region that we were integrating over. We partitioned that into delta x's and delta y's, little rectangles. We took that and multiplied by the height to get the volume of each rectangular solid. We added all of those up along the x and along the y. We did the limit as the norm of the partition went to 0, which means we divided it into more and more and more little rectangles, and that was our definition of the double integral. So now we're going to take the curve given as the vector valued function r, and we're going to partition that curve, and we're going to take a look at the length of each partition, which we'll call delta s. Now, the points along that curve you can think of as being mapped onto a number line, t, and so we're looking at a particular interval of t that gives us that particular arc length. And so we can choose any point in the interval and set up a sum where we're adding up all of the small partitions of the curve. So if we take a function that's defined on the curve, which we called c, then if we multiply the function value times the arc length, we get an area, which we can add up over the entire partition. And if we do the limit of that, as the norm of the partition goes to 0, we get the integral, which we call the line integral. Let's take a look at this example of a line integral. So we're doing the line integral of the function 2 plus x squared y over the curve described as the upper half of the circle, x squared plus y squared equals 1. So here is the upper half of the unit circle. In order to evaluate this from the definition, we have to have an s, in other words, arc length. So we have to parameterize this by arc length. We saw that in an earlier chapter. That is usually not a simple thing to do. However, for this particular curve that I've selected, circle with a radius of 1, it is pretty easy because the arc length and the angle theta is the same when the radius is 1. And so we can use our polar versions of x and y with the parameter s, and that is our parameterization by arc length. So we simply take our integral, substitute the values for x and y, cosine s and sine s, and then integrate that from 0 to pi. Usually, however, we're going to be given curves that aren't nice and easy to parameterize by arc length. They'll be given in terms of a vector valued function of t. And so, using the arc length function that we developed in an earlier chapter, remember this is a function of t, and u is simply a dummy variable to allow us to define s as the integral. And so really all we're going to be doing with this is the derivative. The derivative of s with respect to t would be the magnitude of r prime of t. We did this before. We're just taking the integral that s is defined as and replacing the u with t in the integrand. And so this is another version of a line integral that is easier to compute. So let's see how that works. We're going to do the integral of the function 2 plus x squared y over the curve described as the line segment r equals t comma 2t from t equals 0 to t equals 1. Here's a graph of the curve that we're integrating over. And so we're going to do r prime of t, the derivative of r. We're going to do the magnitude of that. And we're going to rewrite our integral. The ds becomes the square root of 5 dt. And we replace the x with the t and the y with the 2t. And we get this integral, which we can then evaluate. Now that same formula holds true even when we move to 3 dimensions. Here we're integrating the function xy plus 2z over the curve described as 1 minus t, comma t, comma t. So three-dimensional curve. I'm not going to bother drawing the graph of that. However, same process. We're going to replace the x with 1 minus t, y with t, z with t. We're going to replace the ds with the square root of 3 dt. And then we can evaluate that integral.